Hello everyone. So in the last video, we have talked about that how the whole merge sort thing is working. We have talked about this whole code. What is the merge sort function, how this merge function is working, everything in very detailed manner. So I would recommend you to first watch that video first for absolute clarity of understanding. Then you come back to this video for the time complexity analysis of merge sort. So here we will be looking how we can form the recurrence relation. And why recurrence relation? First of all, because this is a recursive function. I have talked about this in detail in the previous video, that because merge sort is a recursive function, it is calling itself again and again. So that's why we need to form a recurrence relation to make sure we are understanding or getting the, say, time complexity. So see what is happening. This merge sort is calling itself. And how? It was initially taking the entire array of size n and it was dividing into two parts. Okay, initially it was, say, the entire size n array, then it was dividing into two parts, then again it was dividing into two parts, and so on. So if this is the whole array, this particular thing was used for the left part and this particular thing was used for the right part. Correct? So if this was t of n that we are trying to generate the time complexity, we are trying to see the time for n elements in the array, we are passing the n elements, then this merge sort function was taking t of n by 2 because exactly we are dividing per the mid position. So if there were total 16 elements, so it would be divided at 8 and 8, then it would be 4 and 4. So this particular left part was for tn by 2, it would be taking tn by 2, and this particular left part would be again taking right part would be again taking n by 2. That's how it is happening. If it was 16, then 8, 8. Left was 8, right was 8. So tn by 2, tn by 2. Right? So we are calculating for this particular merge sort function step by step, line by line, because this if it's a checking, it's a constant amount of time. This is just a variable. This is also constant amount of time, and we're not bothered about these things. We are bothered about the things where it is taking the mass amount of time. There is some recursive call, there is some other function call. So here there are two recursive calls and both are taking tn by 2. Why? Because the subproblem is getting divided into equally two parts. If this was n, it is n by 2, it is n by 2. It is for the left, it is for the right. Now there is a merge call, this merge function call. So we need to go back to the merge function call and need to see what is the time complexity. Then we can write it in arrow manner, that what is it is taking, right? So, or what we can say from this line, if there is a subproblem of size tn by 2 and there is another subproblem of size n by 2, to merge these two subarrays, what is the extra work needed? That will be written over here. So let us see what is the time complexity for this merge function. Now if you can see this merge function only, there is no recursive calls. It is a complete iterative manner function written. What this function is doing, I have talked rigorously. Okay, you can check the previous video. But for the time being, I will be just making you understand what is the time complexity. If you can say this n1 and n2, what this was doing, this n1 was holding this particular part and this n2 was holding this particular part. We are dividing one when trying to merge the final two subarrays. The left subarray was being held by one array, that is L, and the right subarray was held by, this was the left subarray, this is for the left subarray, and this is for the right subarray. So if you can check, the left subarray was running till n1 and the right subarray was running till n2. So initially, if the array size was 16 and if you are trying to merge two subarrays of size 8, then n1 is size 8 and n2 is size 8. That means n1 plus n2 is equals to 16 and nothing but the entire array. Nothing but the entire array. This one. Right? So for this for loop will be taking order of n1 and this for loop will be taking order of n2. If you sum this is nothing but n1 plus n2, order of n1 plus n2, because these are separate for loops. This is not nested. This is one for loop, this is outside this for loop. So it is order of n1 plus n2. So this is order of n total, because n1 plus n2 is nothing but n. Now if you can check this while loop, it is taking I less than n1 and j less than n2. In worst case, this particular thing will run till n1 plus n2 because I will run till n1 whole, then n2 whole, right? In worst case, this will run till n1 plus n2, then again order of n1 plus n2. So it is nothing but order of n, right? So this is again order of n, this particular part. This is again order of n, or order of n1 plus n2, which justifies it is order of n. For this particular copying part, it is again order of n. Now for this while loop, it is running till I less than n1, and this is j less than n2. So this is order of n1, and this is order of n2. Again, if we sum these two, because these two are separate while loops, not nested, once again, so it would be again order of n1 plus order of n2 is nothing but order of n. So if you can check like that, it is order of n plus order of n plus again order of n, summing up these two. So it is order of n plus n plus n. If you can think like that. So it is nothing but 3n. So what we can write, it is order of n, because the power that matters and the power is 1. So it is nothing but order of n. So what we are trying to say, that to merge two subarray of size n by 2 and n by 2, we need n amount of extra work, because this merge function is done, or this merge function is taking n amount of time. So to merge the subarrays of size n by 2 and n by 2, we need n amount of extra work. This n amount of work is needed to merge this. So what is exactly the time taken? If we want to write, it becomes T of n is equals to T of n by 2 plus T of n by 2. That is 2T n by 2 plus n. And there is some constant time. I am just ignoring for the time. So this T of n is equals to 2T n by 2 plus n. So this is the recurrence relation, right? So if this is the recurrence relation, we can solve this using three methods. As you have checked, if you have checked the previous videos, you can understand there are three methods at least to solve this kind of recurrence relation. One is the substitution method, another is the recursion tree method, another is the master's theorem. So in this video, we can solve this particular thing using three ways. What are the three ways? The number one is substitution, the number two is recursion tree, and the number three is master's theorem. So for this recursion tree part, I have already solved this equation when I talked about the recursion tree, how the recursion tree is working and all the procedures. There I took this example. You can check the video number 16 from this playlist, DAA 16, that video. There I have solved this using the recursion tree. So for the time being, let us understand how we can solve this using the substitution method. I have also solved several equations using substitution method. You can check those videos as well. For the time being, let us understand how we can solve this using substitution method. So as there is Tn by 2 inside this equation, so we need to find out, we need to replace this Tn by this n by n by 2. So what is that? That is T of n by 2 is nothing but, we are replacing this n by n by 2. That is 2T n by 2, that is n by 4, plus n is getting replaced by n by 2, so this will be also replaced by n by 2. Right? So T of n equals to 2T n by 2 plus n. This was the earlier equation. Now we are getting T of n by 2 equals to 2T n by 4 plus n by 2. Now there is n by 4. So we can also write T of n by 4 is equals to, if you can check, if you really want to write here, 2T, we are replacing n by 4. So it is 2T n by 4 by 2, n by 4 into 2, that is n by 8 plus n by 4, because we are replacing this n by 4, so it would be n by 2 into 4, that is n by 8 plus n by 4, right? Now if you replace this value, because there is T n by 4, if you replace this particular value here, so what would be? It is T of n by 2, T of n by 2 is nothing but 2T, 2 into, what is the value of T of n by 4? This is the value of T of n by 4. This is the value of T of n by 4, this whole thing. So 2 into 2T n by 8 plus n by 4. This is the value for n by T n by 4. this whole value, and there is also n by 2. So if you really want to do this, it is 40 n by 8 plus 2 into n by 4, that is n by 2 plus n by 2. N by 2. So it is nothing but 40 n by 8 plus n, right? So this is the value 40 n by 2, right? And we can replace this value from here to here. So if you really want to replace, what is the Tn now? T of n equals to 2 into T of n by 2. What is the value of n by 2? T of n by 2, this one. So we are writing 40 n by 8 plus n. This is the value for n by 2, Tn by 2, and there is also a plus n, right? So this is nothing but 8t n by 8 plus 2n plus n, that is plus 3n. Right? So T of n is nothing but 8t n by 8 plus 3n. So you can keep on repeating, you can keep on substituting. That's why this name of this method is substitution. Now if you do that, you can find the pattern. When it will stop, after which step it will stop, right? Suppose after kth step it will stop. After kth step it will stop. So after the third step, we can see this is the equation. T of n equals to 8t n by 8 plus 3n. So after kth step, what will be the in general equation? This will be k of n or kn, and this is, if this is 3, you can see when this was 2, it was 4, like that. So if it is 3, then what is the value? If it is 3, then it is 2 to the power 3. So it is nothing but 2 to the power k. 2 to the power k t n by 2 to the power k plus k of n. If it is stopping at kth step, this is the in general equation. That is 2 to the power k into t of n by 2 to the power k plus k into n. This is the in general equation for that. Now, when it will stop, again the same question. What is the base condition? As we have checked in the previous video, when there is only one element left, that is this particular part, when it becomes 1, t of 1, t of n by 2, t of n by 4, t of n by 8, when it will stop? When there is only one element. So it becomes 1. That means when n by 2 to the power k is equals to 1. That means n equals to 2 to the power k, or k equals to log n. If we take log on both sides, so k becomes log n. So it is nothing but 2 to the power k is nothing but n. 2 to the power k is nothing but n. So replacing this by n. T of n by 2 to the power k is 1. So t of 1 plus what is the value of k? Log n into n. So if you can see, this t of n is 1. So it is n plus n log n. So what is the time complexity? Is nothing but big O of n log n. So this is the time complexity for merge sort using substitution method for the recurrence relation, this one. Now as I have said, for the second one, that is recursion tree, I have already talked, you can see in the previous video, that is I will also pin that particular link in the description, that this is available in video number 16 of this playlist. And for Master's theorem, if you really want to, if you have already watched the Master's theorem videos, you can understand the Master's theorem follows this particular thing. T of n equals to a of t of n by b plus f of n. So here, what is the value of a? A is 2. What is the value of b? B is also 2. And what is f of n? F of n is nothing but this one. So n, right? So we calculate n to the power log a base b. That is nothing but n to the power log 2 base 2. That is nothing but n. So here this particular f of n and n to the power log a base b both are equal. So it follows case 2. And what is case 2? Case 2 is nothing but big O of n to the power log a base b or b base a base b into log n. So that is nothing but this is n into log n. So this comes as order of n log n. So you can solve, if you have a recurrence relation, you can solve it using minimum 3 techniques. That is Master's theorem. Either you can use basic or advanced. You can check out the videos already available. I have already solved this equation in Master's theorem as well. You can check out that how it is coming in detail if you want to find out in detail, because here I have done it just in some time. and we can also solve it using substitution. We can also solve it using recursion tree method, right? So that is all about the time complexity of merge sort. I hope it is clear to you all. And the time complexity for merge sort is order of n log n for best case, worst case, and average case, all the cases. So that's why it is some way useful than some other sorting algorithm, because you're taking in worst case, because we will be considering only the worst case scenarios in real life we should consider. So in other sorting it was taking order of n square, but here it is taking order of n log n. So it is better, but there are some time space trade-off, because for doing that merge sort is taking some extra auxiliary space and all these things. So for to take it in order of n log n, it is using up some extra space as well. So if you have a proper time space trade-off, then you can understand where to use merge sort and where not to. But it is usually, as it is following the divide and conquer approach, so it fits really well when the data is really large. We can divide it and we can solve it, and for solving, after solving, we get this as recursion, the recurrence relation, and we can, when we solve it, we get the time complexity as order of n log n. No matter why whether solving using substitution or recursion tree or Master's theorem, we will be getting order of n log n. So that's all about the time complexity of Master's theorem. I hope you have understood these concepts. Thank you for watching and stay tuned for the next videos.